Good morning, everyone, and welcome to our PCS seminar. So our today's speaker is Dr. Dominik Šafránek. Dominik got his PhD in 2016 from the University of Nottingham, where he worked on quantum metrology mainly. And after his PhD, he moved on in 2016 itself to the University of California in Santa Cruz, where he initially worked with the Foundational Questions Institute, where I think he was involved in a very interesting program called the Physics of the Observer. So in this program, what they were trying to understand is how the observer plays a role in quantum thermodynamics. And I think this is also something that he will talk to us about today, where he will introduce the notion of this so-called observational entropy, which he and his other colleagues have put forth in the last few years. So with this, I would like to welcome Dominik and give the floor over to him.
Thank you, Cesar, for the introduction. All right, so this picture, that's from Pulp Fiction, and you can see you see Santa Cruz logo there with a banana slug. So this is where I was past almost 4 years. And this work started over a discussion with Anthony Aguirre and Josh Deutsch. Anthony Aguirre is a cosmologist, and Josh Deutsch is a condensed matter theorist and biophysicist. And over the years, we also included Joe Schindler and Dana Fayez, who were PhD students, both recently graduated, and Joe is now a postdoc. So what I'm going to talk about, first I will go over some Entropy Zoo. I will not mention all of the entropies, but I will mention some of the entropies that seem somewhat relevant. Then I'm going to introduce observational entropy. I'm going to start introducing with a game, so you'll get some intuition what it is about. I'll define what a question is mathematically, what is an answer, and how all of these things can be mathematically described. And as a prize for playing that game, we're gonna define observer's uncertainty, which we will call observational entropy, and we will show some properties of the definitions. Then we'll move to applications in thermodynamics, and I specifically focus on two of them. The first is a new definition of equilibrium entropy that's based on this framework of observational entropy. And the second will be a definition of non-equilibrium entropy, which has pretty cool properties, which I don't think many other entropies out there have. And finally, I'll summarize and say in which fields I think this framework can be applied. All right. Okay, so before we go to Entropy Zoo, let me just mention this nice quote from John von Neumann to Claude Shannon. So after Claude Shannon, I think it's in 50s or 60s, introduces Shannon entropy, John von Neumann mentioned to him that he already studied this and suggested that he calls it entropy because first of all, this has been studied. Actually, von Neumann himself introduced von Neumann entropy much earlier than Shannon in 1929, the latest, maybe 1926, something like that. And more importantly, he said that since nobody knows what entropy really is, Claude Shannon will always have the advantage. And I think many people actually took this suggestion to the heart and started calling things entropy. So that's why I'm going to talk about Entropy Zoo right now. So I usually say there's like 105 entropy definitions. Here I mention just, I don't know, maybe like 20 of them. So there are some coarse-graining based entropies. So entropy that, the uncertainty, which is usually what entropy measures, is given by somewhat coarse-grained description of the system. Then there are entropies that appear from a thermodynamic perspective from heat exchange, studying heat and particle exchange between different systems, heat baths. And that these have been actually introduced in around 1870 by various people, namely Clausius, but then Boltzmann and Gibbs and Sermel. Then there are quantum information entropies. These actually predate classical information entropies by a few decades. Mostly work on by von Neumann. And then we have information entropies, which are studied mostly in the 60s and still to these days. So observational entropy falls into the set of coarse-graining base entropies, and it relates to many of those entropies that I showed here. And more specifically, it generalizes Boltzmann entropy and coarse-graining entropy. Coarse-graining entropy has actually appeared several times in literature before. Sometimes it was given this name, sometimes it wasn't named. But I found that this is basically a concept that has appeared since maybe 60s. And observation is generalized coarse-graining entropy and also Boltzmann entropy. Not the definition with just energy coarse-graining, which is the something which is called surface microcanonical entropy, but it generalized also the one that the coarse-graining is considered to be general. And then these blue boxed entropies are the ones that observational entropy directly relates to. So this is a part of what this talk is going to be about. So now that I gave you a bit of context, let me introduce the game, which will lead to definition of observational entropy. So you're gonna play "Who is it?" game. I'll ask you to guess a famous person that I'm thinking about. So let's say there are 5,000 famous people, maybe about 3,000 men, 2,000 women. I don't know if that number is correct, but I'm just assuming that. So you can, in order to guess which person am I thinking about, you can ask, is it a man or is it a woman? And I say, yes, it's a man. And then your uncertainty will go to from 5,000 to 3,000 people. Then you can ask further, let's say, which nationality is he? And I say, well, he's Austrian. And that cuts it quite significantly to 80 people. And then you can ask me, what is his profession? He's a physicist. And, you know, there's a good number of famous Austrian physicists. I will guess 7 at least. And if you ask me what is he known for, I tell you entropy. And maybe many of you have already guessed that the person I was thinking about is Boltzmann. So how does this work mathematically? So I defined some set, which was in this example, a set of famous people. This can be general set. So this can be general set, or in physics, it can be phase space, or in quantum physics, it can be Hilbert space. Then there is a question, which is mathematically is actually a coarse-graining. And this is not very intuitive, but a question really mathematically is sensibly defined as a set of disjoint subset of the set of famous people. So basically, question is defined by the collections of its answers, at least mathematically. This is what seems to make some sense. The answer, if I told you, okay, yes, he's a man, that defines a macro state. So that is the subset, and that's the element of the coarse-graining. And the famous person would be a micro state. That's element of the set. And more generally, both in classical quantum physics, it can be either phase space density or just some probability distribution or density matrix. That is usually not called a microstate anymore. So as an example, So how would you measure uncertainty that you have given these, that you asked these questions and received some answers? So let's say if you ask, is it a man? So the coarse-graining is given by the question of, is it a man? On this microstate, then I'm going to define uncertainty as a logarithm of a number of microstates in that given macrostate. So this is the subset of the coarse-graining, and it has some number of constituents. So if it is a man, then the volume will be volume of the macrostate of yes, and if it is a woman, it will be volume of the microstate or no. So on the example of a man, you are going to define the uncertainty that you will have after asking that question as a logarithm of 3000. If, for example, you ask that question, I was thinking of my favorite physicist, Eminator, then the logarithm would be logarithm of volume of macrostate P no, and that would be a logarithm of 2000. And of course, you can generalize this to multiple questions, or I could rather say multiple coarse-grainings. So if you first ask, is it a man and which nationality is he? Then the uncertainty is going to be logarithm of volume of the overlap of the two sets, and that's going to give you a logarithm of 80. Now, why I say it's going to be a logarithm? That's because logarithm has a very nice property that logarithm of multiple of two numbers is the sum of the logarithms, which is really useful of defining some quantity that is additive. I could choose something else, and that's what Rene entropy does, for example, but I'm going to stick to just a simple logarithm. So this was fairly classical, a classical example of just a simple guessing game. But sometimes the answer is not definite because there might be some uncertainty in the microstate. For example, you can ask me, did this person always have a beard? And actually, I don't know whether Boltzmann always had a beard. I mean, after he reached adulthood, I would say yes, but nobody really knows this, and nobody knows whether Boltzmann shaved himself maybe this one time on a vacation. So this is some kind of classical uncertainty because there is some definite answer, but we just don't know the answer. But then there is some quantum uncertainty that can also happen, and this is quite of a different nature because there is some inherent uncertainty in this. For example, if I have a perfect knowledge of a position of a particle, that I cannot have a perfect knowledge of its energy, because energy eigenstate does not have a definite position the other way around, because position operator usually doesn't commute with Hamiltonian. So how do I treat this? Well, we need to add this additional uncertainty that comes from stemming from this uncertainty. So assuming that probability that Boltzmann always had a beard is 90%, which means that there is this probability we define 1 minus probability no, it's 0.9. Then if we ask about Boltzmann whether he always had a beard, what's a sensible thing to do, and there are some alternatives, but what is a sensible thing to do here is to average the average uncertainty you would get after learning the answer, but also there is some uncertainty that you have when you are asking the question itself, because you don't know what I'm going to say, and that's going to be the uncertainty from receiving an indefinite answer. So you can see that this is basically Shannon entropy. So what I'm going to define, you can generalize, of course, this to multiple coarse-grainings or multiple questions. So I'll define observer's uncertainty about the state of the system when asking a series of questions that are C1 up to Cn in this order, and we define it as the as the mean uncertainty after learning the answers plus this additional uncertainty from receiving indefinite answers. So this is the volume of the macro state. This is what we call the volume. That's basically a number of constituents, at least in classical examples. And this P is a probability of receiving answers I1 up to In in this order. The order doesn't really matter in classical systems, but it does matter in quantum systems. Alternatively, we can view this as the mean Boltzmann entropy. So if you have a general macro state with some general coarse-graining, this is going to be a volume of a macro state. And this logarithm of this volume is what you can call the Boltzmann entropy. And then you average it over the possible answers. So this is the mean Boltzmann entropy. And this part is the Shannon entropy, which defines uncertainty with receiving some outcome, or rather in this case, a vector of outcomes. And from a physical perspective, you can actually call this the mean uncertainty in a macro state. And this is the mean uncertainty into which macro state the microstate belongs to. So if my microstate is Boltzmann, then this is really not knowing, whether he's an Austrian or let's say German. And this is not knowing what this corresponds to not knowing whether he's famous for entropy or something else. Yeah, so I think this gives you an idea what observer's uncertainty is, and this is actually what we define as observational entropy. To get you even more intuition, I will show you an alternative derivation which might make more sense. So assuming that observer cannot distinguish between different microstates within the same macrostate. So let's say this is one macrostate. This was the man macrostate. This is the woman macrostate. Then if I'm thinking of a man, I cannot distinguish between different men within this macrostate. If I ask just question about whether it's a man or a woman, it doesn't distinguish between different men. So I can get some probability that, well, the observer that asks me will know some probability with what I can tell him whether it's man, or the probability that I can tell him or her that it's a woman. Then not being able to differentiate between these different microstates, in this guy and this guy, the sensible thing to do is take the full probability and divide it by the number of constituents, by the volume of the macrostate. And then if you take Shannon entropy of these microstates, but with this prescription, you plug that in, you sum or all microstates within one macrostate, that's just going to pop out this VI here that cancels, and that defines observational entropy. So this is very similar to a construction of Boltzmann. Okay, so now that we introduced observational entropy, let me get to some of its properties. Well, one of the properties that makes sense is that if you ask one question about the system, you will get some value of uncertainty that you will have in asking that question. But if you ask one more question, your uncertainty might decrease. Well, at least it's not going to increase. And you can ask more questions, and then your uncertainty will continue to decrease, or at least will not ever increase. So this is basically a mathematical theorem that says that if you ask more questions, you will get to know more. On the example, first I asked, is it a man? That I was up to a logarithm of 3000. Then I asked which nationality is he? That was logarithm of 80. Then is he a physicist? And this was what is he famous for?
Oh, Dominik, sorry, just a quick question here. So you are somehow assuming that the questions that you ask have a definitive answer, right, to it? Because what if the questions that you ask do not have a definite, I mean, all the questions you ask do not have a definitive answer? Why is it then necessary that you would have such inequalities?
Oh, that's a good question. Well, actually, I don't assume that. This works generally. So this thing is just an example.
Okay.
But this theorem holds generally even with indefinite answers, and even in quantum physics, even when these coarse grainings do not commute.
I see.
So this is completely general.
I see. Okay.
I have an add-on question to that. Can you transfer question into something we use in physics, a term in physics or mathematics? What is that? Is it a measurement in physics, or is it what is
exactly? Yeah, I was going to talk about that a little later in the talk, but since you asked, in physics, a coarse graining is defined by a measurement, and a measurement is defined by some observable. So if you take spectral composition of some observable, that really observable defines, or is mathematical description of the measuring apparatus, and the measurement itself is related to the projectors in that spectral composition of that observable.
And what would it what would this question be in mathematics?
Well, that would be given by the eigenvectors of that observable.
Well, I meant more like the process. When you ask a question, then you get an answer. So what is the mathematical analog of asking a question? What do you do? It must be some operation. What an operation of what on what?
Oh yeah, okay, I see. Yeah, so this quantity, this observational entropy, actually measures uncertainty about the initial state if you were to make a measurement, not that you are actually making it. So it's as if you would ask, if I were to make a measurement right now, what would be my resulting uncertainty about the state of the system? If I actually made a measurement, then I would collapse the state of the system, and my uncertainty would be a little bit less, usually. Might not be.
Thank you.
Yeah, so the causing is definitely defined by a measurement.
Okay, thanks a lot, Dominik.
Okay. So to conclude this, additional questions reduce the uncertainty. And now we can ask, where does it end? How much can you know? And well, there is an upper and lower bound. So before I defined a set of questions that, in the example I gave, the set was the set of famous people. So that was my general set, but in physics, we usually take phase space, or in quantum physics, we take Hilbert space. And logarithm of the volume of this set, which in case of Hilbert space is the dimension of the Hilbert space, is what upper bounds the uncertainty. That kind of makes sense, because this is the maximal uncertainty that you can have given the size of the set. And the lower bound is given by von Neumann entropy, or the Gibbs entropy in classical systems, which for systems that are not defined on phase space is called differential entropy. So this von Neumann entropy or Gibbs entropy defines inherent uncertainty due to the state being in a mixed state. And that can come either as in the form of classical uncertainty, meaning that you somehow lost information that you had before, but now you don't have it, or it can be inherent. For example, if you take a subsystem of a pure state that is entangled, then you will have some inherent uncertainty coming from the fact that it's entangled and you don't have the access to the other part of the system. So this is the von Neumann entropy. This is the minimal uncertainty that you can have about the system. So in our example, this was logarithm 5000, and this was logarithm 1, which is 0 in the case that I gave. Not considering example, just considering a little bit more general systems. If you ask second question, you might reduce the uncertainty, but you might not. So the question is, when you don't reduce the uncertainty? Well, this has been also mathematically proved that, for example, you don't reduce the uncertainty if question C2 has been already answered by answering C1. And secondly, you will not reduce uncertainty if you already reached the minimal inherent uncertainty. If you know already everything that is known to be known about the rho, then you cannot reduce the uncertainty. So that's another example where the additional coarse-graining doesn't help. So these are in classical systems. Actually, in classical, there should be Gibbs entropy here. And then in quantum systems, there are other cases where this can happen. For example, if sometimes you can measure something, let's say you measure position perfectly, which you actually cannot do, but okay, let's say you measure energy perfectly, you identify the energy eigenstate. Then, even if you ask any other questions, you already destroyed all the information that's been in the system. So whatever question you ask afterwards is not going to reduce your uncertainty. This also leads to this phenomena that can be called in quantum physics, and I have a very classical example here. But this doesn't have classic physics. Let's say some Wunun expresses love to this guy, and he asks, well, are you too old for this? Well, she feels refused, and she's just gonna leave, right? Nobody wants to hear this. Which can be summarized: asking some questions prevents you from getting to know more. This is the example I came up with, but really this is stated about quantum physics. So if you ask some questions about, you make some measurements, and then you make some other, you might not learn as much. And again, in quantum physics, order of questions matters. This is because different coarse-grainings do not commute. And you can also realize that the first coarse-graining is more important than the second one because it uncovers more about the question you ask. While the second one is just taking scraps from what hasn't been destroyed before by asking C1. Okay, well, what is this good for, apart from describing games, as I did? For example, by describing entropy increase in isolated systems, and also more technical one, this gives a new way of defining equilibrium entropy. And even more interestingly, at least to me personally, is that this allows to define non-equilibrium thermodynamic entropy, which kind of makes sense. And there's been this long-standing question: which entropy is relevant for isolated quantum systems? Why is this long-standing question? Well, there are many entropies, as I showed you before, and it's not really clear which one is the one that really says, okay, when we talk intuitively about entropy increase, which is the one that increases? Because as you probably know, the second thermodynamic law is saying that entropy increases in an isolated system, but then you can ask which entropy increases, because fundamental entropy doesn't increase. Then you can ask, well, maybe there's a different entropy that increases. One of the entropies that increases is entanglement entropy, but then you can ask, does it have a good behavior? Is it additive, for example? And that's where the observational entropy comes in. Defining entropy production does not explicitly depend on temperature and allows for general state of bath. So this is applications for open systems, and I will talk about this. There is another work related to open systems, but this was studied by Philip Strasberg, who is now in Barcelona. He put out 2 papers on the archive about the open systems, but I will focus on these 3. And there's much more that this is able to do. So this entropy, since it is generalization of Boltzmann entropy, you would assume, well, it has pretty much the same properties, and indeed it does. It will typically increase in isolated systems. And it will increase just because of how it is constructed. It increases pretty much no matter which coarse-graining you choose. Because naturally, the state will tend to macrostates that have higher volume. So if you start in some macrostate that have small volume, if you wait long enough, your state will most likely end up in some large macrostate or several large macrostates.
Sorry, let me ask you a question. What do you specifically mean? So I have an isolated system, I have a microstate.
Mm-hmm.
Okay, so that thing is just evolving in time and is still a microstate which changes in time. What do you mean by macrostate here? How do I map from a micro to a macro? By coarse-graining, is that what you mean?
Yeah, exactly. So coarse-graining is a set of subsets in classical physics, or simple subsets of phase space. In quantum physics, it's you assume that your Hilbert space you can write it as the direct sum of Hilbert spaces, and those smaller Hilbert spaces will be your macrostates.
So it's coarse-graining, and then you define a macrostate in this coarse-grained space. I don't know how to call it, and then okay. And then you start calculating entropies, and then they of course change in time. Yeah, thank you.
Yeah, and it increases usually, and
usually,
it can also decrease, although
it has to by the Poincaré recurrence theorem.
Exactly. Yeah, you answered it for me. It has to. Yeah, and I think actually this is quite nice that it can increase because these things are not unknown. You have something called logarithmic echo. This has been observed in experiments, and usually in our everyday lives you don't see this entropy decrease, but it doesn't mean that it shouldn't be described by the theory. So this goes against what some people believe, that entropy must always increase, which is I think widely held belief in several fields. But it's just physically not true that it should always increase. Okay, let me get to the second application. That's a new way of defining equilibrium entropy. So you probably know microcanonical entropy. Here, this is what is sometimes called Boltzmann entropy or surface microcanonical entropy. And that's defined for system at energy, some fixed energy E, at the spatial volume V, and with number of particles n as the logarithm of energy density of states times time energy width. It doesn't really matter. This energy width is not really that important there. It's there mostly for proper units, because you see this is a multiple, so you can rewrite this as the sum of the two, and this is exponentially in size of the system. So that turns out to be just additive constant, but it's pretty important there just for the units. Together, these two things is a number of states in an energy shell. So this is what is usually called microcanonical entropy. Given this framework of observational entropy, you can generalize this notion, which we called equilibrium thermodynamic entropy. So you see this depends on the energy and on the particle number, and there is some volume. And we forget the volume for now, but energy and particle number can be measured. Doesn't it make sense then that equilibrium thermodynamic entropy could be defined with energy and particle number coarse-graining then? And when does this actually make sense? Well, for systems that conserve number of particles and conserve number of energy, this equilibrium thermodynamic entropy will be constant. That's simply because any coarse-graining that commutes with the Hamiltonian will lead to constant observational entropy. So if you take any coarse-graining and globally conserved variables, you will get some constant observational entropy. And if you, so in this case, if I take energy coarse-graining and number coarse-graining, so this corresponds to measurement the number of particles and measuring number of energy. And here I need to stress that the energy is measured with some fixed resolution delta E. This delta E corresponds to this delta E. And how does this generalize macroeconomical entropy? Well, if you put inside the common eigenstate of the particle, or the number operator and Hamiltonian, you plug it in, it's just gonna give you exactly the same formula. If you insert inside microcanonical ensemble, microcanonical density matrix, it gives you also the same formula. You know, there'll be some correction between this and that, but it is going to be small. If you put in insert canonical ensemble, it's going to give you canonical entropy. Each inset of or fixed energy depends on temperature, or you could put mean energy here. And you can also put grand canonical ensemble, and this generalizes to grand canonical entropy. And of course, if you have more conserved quantities in an isolated system, you can add more coarse-grainings here. Let's say your total spin is conserved, you add that in, and if you put generalized ensemble into it, it's going to correspond to the generalized entropy. So by just defining this equilibrium thermodynamic entropy with this coarse-graining, I can just generalize all sorts of equilibrium entropies with a single formula. And every time I put an ensemble into it, I'm going to get the corresponding entropy. Now, second application would be defining non-equilibrium thermodynamic entropy. Now, let me give you an example here. So usually when people talk about entropy increase, they usually just mean, okay, it's the system starts at some low entropy state, which is here. And then something happens and entropy increases, and then it's high entropy state. And we know how to define entropy for each of those two situations. So here we just say, well, these two systems are not really interacting. They have no shared history. The entropy is going to be just the sum of two entropies, sum of the two equilibrium entropies. And then if you remove the partition and the particles start to mix and expand, at some point it's going to equilibrate. And that's when you say, well, I know how to associate entropy to this one. That's going to be the total thermodynamic entropy of the system A plus B. But this distinction, actually entropy with this sort of assignment increases not continuously from this entire process. It actually jumps as soon as you remove the partition. And why does it jump? Because by removing the partition, you immediately changed the Hamiltonian of the system. Well, you change the boundary condition. Or that those two things are equal. So either you change the Hamiltonian of the system or you change the boundary condition. And that changes the definition of entropy, at least the way it is defined here. So you can say, well, entropy was low, and then I removed the partition and entropy was high. And then, you know, if you are really quick enough, you can insert the partition just here, and the entropy would just jump low again. But we want to do something better. We want to have a single formula that works for either of those cases, but also makes sense in between. Something that starts as the sum of thermodynamic entropies, and then when you remove the partition, in increases until it reaches some value that is very close to the equilibrium entropy of the full system as the system thermalizes. And how do we define that? Well, since equilibrium thermodynamic entropy is defined by global conserved quantities, and those remains constant, in order to define something that happens on time, something that changes, you really need to introduce dependence on local instead of global variables. This is this is because when you say, oh, entropy increase, it's just meaning, well, if I stir a bowl of something, or if I put some milk into my coffee and stir it, that I can see that milk and coffee, which were separated, are suddenly mixing together. So what I call entropy increase in that is really I'm distinguishing the milk and the coffee. So introducing the dependence on the local instead of global variables, I can talk about entropy increase. So I simply define non-equilibrium thermodynamic entropy as the observational entropy with coarse-graining that are first given in local particle numbers and then local energies. In common systems that consider the number of particles locally, the particle operator commutes with the local Hamiltonian operator, and which means that it doesn't really matter in which order you pick this one or that one. You can switch the order and it's not going to matter. In some cases, when the local particle numbers and local Hamiltonians do not commute, it will depend on the order. So this entropy is really corresponding to local number of particles and measuring local number of particles and measuring local energies. We did some simulations. So imagine you have the system, you measure the local number of particles, which is about 10 here, about 3 here, you measure local energies. And you will calculate this non-equilibrium thermodynamic entropy on the system. So here I introduce, here I have 2 curves. I think this one corresponds to the blue curve. The red one is a relative quantity, which is just coarse-graining in local particle numbers by global energy, which also behaves very similarly in some situation. But I will not talk about this one here. So you can see that if you start this green line here, that's the equilibrium entropy defined by the formula that I mentioned before, the microeconomic entropy. And you can see that first you have some fluctuating entropy. This is because I divided the system into 4 parts in total. And then from the first 2 parts, the particles spread into the other 2 parts, that's here. When I remove the partition as in this example, and the entropy very quickly increases to some value that's fairly close to this thermodynamic entropy, as I was saying that I'm going to do. So this formula really generalizes equilibrium entropy, but also is capable of increasing, and it's a single formula that doesn't change throughout the system. And why it doesn't change is because it doesn't depend on global Hamiltonian that changes these conditions, but on the local parts. And you don't need to change this definition in order to get to the proper thermodynamic entropy. This is a same simulation on the classical system. This is actually, again, the relative quantity, but for the situation also here, these 2, this one and the one that's here, they behave exactly the same. So we initialized some particles in a corner of our 2-dimensional phase space. Well, configuration space in this picture, but really it was modeled in phase space. Then the particles spread, and the corresponding there are actually real snapshots of the simulation. So when the particles seem to spread, then the entropy increases, and when the particles are already everywhere, then the entropy is very close to the thermodynamic entropy. So what are the properties? Well, first of all, this entropy is additive. On this example, if you take a low energy eigenstates or common energy and particle number eigenstates of the local systems, and you take them to be independent, then this non-equilibrium entropy is going to be the sum of local microeconomic entropies. Of course, you can generalize this to any local density matrices. It works exactly the same. If you take a special case where you take Gibbs thermostates as a state of your system, you can actually show that the entropy increase in this definition, the entropy production, corresponds exactly to what you would expect about thermal baths, and that's this is basically the Clausius definition of entropy. So this is the heat flowing to the first system. This is the heat flowing to the second system from the first one, and these are the temperatures of the corresponding baths. So this has been proven by Strasberg in 2 papers. Very beautiful ones, by the way. We have a very interesting bound for this quantity, and so this non-equilibrium entropy is approximately upper bounded by the thermodynamic entropy. This approximately is because there is some interaction part of the Hamiltonian, which is why it's approximate. So actually, if you have strongly interacting systems, it might not hold. But for weakly interacting systems, this holds. And it's lower bounded by the sum of von Neumann, but also something which we called multipartite entanglement entropy, which is a generalization of entanglement entropy. So entanglement entropy is defined only for global pure state and only for bipartite systems as the von Neumann entropy of the reduced state. And also you can actually prove analytically with some fairly difficult math, which uses ansatz of the Hamiltonians of non-integrable systems to be at least the part of Hamiltonian to be approximately described by random matrix. And starting from that point on, you can derive some convergence in the long time limit. This convergence is not really in the mathematical sense. What this convergence means, if you wait a long time, very long time, basically your phases with each energy eigenstate will become as if they were drawn from a random ensemble with uniform distribution. So this is the sense in which this equality, this convergence holds. Of course, as was mentioned by Sergey, there's a Poincare recurrence time where this entropy also increases very close to the initial value. And finally, what is the interpretation of this non-equilibrium thermodynamic entropy? At some intermediate time t, when the system has only partially equilibrated, so let's say we have this in this picture here, this is some t, some snapshot of the system at time t. Its value can be interpreted as the equilibrium thermodynamic entropy the system would attain in the long time limit if, starting from time t, meaning that at time t I do something, the subsystem were not allowed to exchange either energy of particles. So how do you say this in words? Basically, if I take a system at time t and I insert infinitely quickly some wall in between the partitions, I insert some wall here, and assuming I don't affect the system, which is not true in quantum physics, but classical physics it is true. And this wall will forbid both energy and particle exchange between these subsystems. And then I wait long enough, so then in order to be able to define equilibrium entropy for each one of those parts, then this non-equilibrium thermodynamic entropy is going to be equal to the total thermodynamic entropy associated to the system, which is additive if they are not entangled, but it's not exactly additive if they are entangled, but there's some correction that goes into that. So I think this is very nice. This is basically what you would expect of a non-equilibrium thermodynamic entropy. This is my last non-summary slide. So before I showed a zoo of entropies, and I said, well, this observational entropy generalizes some of them and is directly related to some other. So let me go through this list. Boltzmann entropy, that's really defined only for classical systems, non-quantum, where you have, and it's applicable only if you consider microstates of the phase space, which are the points of phase space. So if a point of phase space belongs into some macrostate, then the Boltzmann entropy associated with it is logarithm of the volume of that macrostate. Then if you want to generalize a little further, and you say, well, maybe I don't know exact position and momenta of my particle. I know only the phase space density. Then I don't know exactly into which macrostate the particle belongs to, and I need to add this additional uncertainty that I have about the state of the system. So the coarse-graining entropy has appeared in literature actually since von Neumann. Von Neumann actually introduced something like observational entropy, but only with a single coarse-graining in 1929, saying that von Neumann entropy is not a good definition of thermodynamic entropy because it associates entropy 0 to any pure state. So this was his criticism of his von Neumann entropy, which didn't have that name at the time. And he suggested this entropy instead. And this has appeared in literature, fairly sporadically, but it did appear maybe 10 or 15 times, at least from what I was looking in many parts of the system. Sometimes it was called something, sometimes it wasn't called anything, or just mentioned in passing. So this is what was sometimes called coarse-graining entropy. And observational entropy is a generalization of these two multiple coarse-grainings, which also work for quantum systems and coarse-graining that do not commute. Then you have entropy of a measurement, which has been also called entropy of a partition. So given the measurement, you will just take this first part, the Shannon entropy. This quantity is not very good quantity, very good entropy associated with the system, because as you can see, this is upper bounded by the logarithm of number of measurement outcomes. So if you have two measurement outcomes, this is upper bounded logarithm of 2. That doesn't really make sense if you want to associate logarithm of 2 or something less to a large thermodynamic system. So this is not a very good thermodynamic entropy either. Then, as I mentioned in this talk, the thermodynamic entropies connect to observational entropy of the global particle number coarse-graining and global energy coarse-graining. So if you put any ensemble of density matrix into it, you get the ensemble entropy. The Gibbs entropy, and there are 3 different definitions of what Gibbs entropy means. I chose this one, which is actually has a different name in mathematics called differential entropy. The only difference being that Gibbs entropy has some prefactor there, often connected to Planck units, to Planck constant. So this is the integral over phase space density, something like a Shannon entropy, but over the phase space. And if you take the classical observational entropy, this is the lower bound of the Gibbs entropy. Similarly, von Neumann entropy, as I was saying before, acts as a lower bound in quantum systems. Then Shannon entropy, that's very similar to everything here. That's just P log P standard value, as I showed in our alternative derivation. If you put this specific probability of a microstate, you are going to define observational entropy as well. And now there are some 2 relationships that I didn't talk about a lot. There is a relative entropy, which is also called Cool-Black-Leiber divergence, which is some form of a distance, even though it's not symmetric, but some form of a distance between 2 probability distributions, which is widely used in estimation theory. And observational entropy is, for a finite dimensional system, is given by this maximal uncertainty, the logarithm of the dimension of the Hilbert space, minus relative entropy between the probability outcomes as compared to the probability outcomes you would get if your state would be completely mixed. and that's this VI over dimension of H. This is what completely mixed state will give you. So this is minimal if Pi equals this thing. Then in that case, this is 0. And finally, there is a relationship to entanglement entropy. So this is what is usually standardly defined. In our recent paper, we generalized this to also mixed states and multipartite systems by the formula using observational entropy as the minimum entropy difference between the local coarse-graining. So you see the infimum over all local coarse-grainings minus the minimum over global coarse-graining, which is the minimum entropy. So this entropy gap is what is actually a sensible definition of entanglement entropy, and it actually generalized this formula to mixed and multipartite system. And it's also additive and has other very nice properties. And then if you take observation entropy with just local coarse-graining, that this is greater or equal than the sum of the fundamental entropies and this multipartite entanglement entropy. So now I'm getting to summary. Observational entropy measures the amount of uncertainty about a system from a perspective of an observer making measurements. It has many interesting properties. For example, it can be proven mathematically that more questions lead to more knowledge or less uncertainty. Some of those properties are exhibited only in quantum systems. For example, that order of questions matter, or that sometimes you cannot, you do not, when you ask the wrong questions, you don't achieve the full knowledge. Those somewhat wrong questions are those that do not commute with the density matrix. And it has application in thermodynamics. I was talking about equilibrium, non-equilibrium thermodynamic entropy, but there are also some other ones in open systems. And we were thinking about possible applications to other fields. So as I said before, there are already some applications to open systems. I think this area is still largely unexplored. There are already some fluctuation tolerance for this in open systems. We also think that it can be generalized to information engines. This could also be a good framework of describing generally Gibbs paradox, which is very much connected to observing physics. Basically, to explain that a bit, it talks about whether entropy increases if you, as an observer, have ability to distinguish two types of particle, or you don't, or whether you don't have that ability. So the entropy increase is different depending on observer's ability to do something. And we think this framework could very well describe that. We also think that there could be some good good connection with work extraction in realistic situations. For example, if you just say, well, observer doesn't really have complete control of the system, he or she can do just some macroscopic measurements, or just use piston to do something that will correspond to coarse-grained description of the system, and therefore we think that observation entropy might be somewhat related to amount of work that can be extracted from a system under realistic situations. This whole formalism is also very similar to methods used in a normalization group. Basically, what they do there is they take a local coarse-graining, which in our formalism corresponds to local coarse-grainings, and make them finer and finer, and studying coarse-grained free energies typically, but you can also do coarse-grained entropies. They until they scale exactly the same. That's what is going to give some information about criticality and behavior of the system. Since this framework also didn't assume anything about whether the definitions didn't assume anything whether the system is strongly or weakly interacting, we think that you can as well apply this to strongly interacting systems. The only thing we suspect is going to go wrong is that it might not converge that well. but that might be a very interesting thing to study. Black holes is another area where this can be applied. We already discussed this, not here, but with my coworkers. There's this whole literature on how to define entropy of a black hole, and many scientists talk about entropy of a black hole. Not so many scientists define it, and when they define it, those definitions do not are not always the same. And there's a plethora of discussion about what is the right way of assigning entropy to a black hole. There is this a long-standing question: why does the entropy of the universe increase? I think maybe coarse-graining, this observational entropy might be a good measure of entropy of the universe, although it's still unclear to me how one would define a coarse-graining in the universe. Maybe you heard about Boltzmann brains. That's an idea that maybe the entropy of the universe didn't start slow. Maybe it started high, but we kind of fluctuated into existence by random chance. But you can actually calculate the probability this is going to happen. And there's one other paper we wrote. Yeah, this is pretty out there. So I'm not going to go more into details of that. And there's also a question of how to define entropy of self-gravitating fields, because these are self-gravitating fields are dynamical systems. And you cannot really associate entropy to singularity, because if you have just self-gravitating system, at some point they're going to end up in singularity and everything diverges. So how do you even talk about entropy? You cannot define equilibrium entropy. But maybe when the self-gravitating fields are not yet in a singularity, you can still define observational entropy of this. And maybe there will be a nice description of thermodynamic entropy of these fields, at least before they all collapse into singularity. And that is all from me. I would appreciate and very much like to hear more questions and answer more questions. And these are the papers relevant to our work. And please don't hesitate to contact me if you have some other questions or comments or anything you would like to discuss on this email address. Thank you.
Thanks a lot, Dominik, for this wonderful talk. So the floor is open for questions. Sergey.
Yeah, thanks for this interesting talk. I have one question which starts on page 72, not far from where we are right now. And just go back, please.
Mm-hmm.
Right. So in this little, well, this was, I guess, a classical simulation of some ideal gas. Is that correct?
Well, not so quite ideal, because I wouldn't really thermalize. There was a very small interaction.
You added what, please?
Excuse me?
Yeah, I didn't understand. So is it an ideal? You said, no, it's not an ideal gas. What does it mean? You include interactions between the particles?
Yeah, so ideal gas, since the particles do not bump into each other, they don't really thermalize with an ideal gas.
Yes. But they would still spread over your volume, right? If you
so I think it would also work.
So that's so that actually is my the basis of my question. Do you if you have an integrable system like an ideal gas, but you would look at coarse-graining and then define entropies there, you probably would still see some nice growth of entropy and be happy. On the other side, if you do include some very weak interaction between the particles, if you make it weakly non-integrable, then on a potentially very large time scale, you will, if you look in detail into the dynamics of the system, you will see that the system leaves its whatever n-dimensional, where n is the number of particles, torus in its 2n-dimensional phase space, and starts to wander off somewhere else. And so how is this second potentially very large time scale due to some weak non-integrability popping up in all these studies of non-equilibrium entropies?
Yeah, that's a very good question. I think I have some answer for you. So we actually studied non-equilibrium systems as well in quantum physics. So there's this Hamiltonian that assumes just nearest neighbor interactions and hopping. And those are integrable. And then you have nearest neighbor and next nearest neighbor interactions, and those are non-integrable. So we studied both of those. First of all, non-integrable systems, as you said, they do thermalize as well. I can show you the graph, but I would need to pull out the paper back and maybe send you a link. But basically, let me just tell you what's going to happen. So with a non-integrable system, they basically increases very quickly, and then it kind of stays constant. For an integrable system, what's going to happen, it doesn't increase as quickly. It may go a little bit like this. Then it kind of goes down because that's the part where all the particles, when they are spreading, are reflected from the other wall, and then it increases again and reaches some fairly constant value that fluctuates much more than an integrable system. So it actually works for both non-integrable and integrable, even though integrable do not thermalize as well. And
so what I get from your answer is that for an integrable system, you would have some oscillations initially, fine, but then after long enough times, you will see much larger fluctuations than for a strongly non-integrable system. Is that what you say? The amplitudes of the fluctuations become...
Yeah, that's right. And I think it makes sense because in an integrable system, you have infinitely many conserved quantities. So well, you just don't explore those, entire Hilbert space. And those integrable systems are also much more sensitive to your initial conditions.
Can you quantify these fluctuations depending on the number of integrals of motion you have in your system?
No, I didn't study that, and I wasn't thinking about it. So we actually proved analytically that it converges to global thermodynamic entropy, the equilibrium one, only for non-integrable systems, because with integrable systems, there is no this ansatz. It's not belief. I think it's not true that those would be well described by random matrix theory. And since the derivation assumes that there is this equivalence between random matrix theory and non-integrable systems, we weren't able to prove anything about non-integrable systems. So this is all just suggestion given by the simulation.
Thank you.
I have another question, Dominik. So if we go to quantum thermodynamics, right, and we talk about entropies, the idea typically is that your heat, which comes into your first law and the second law, is sort of, so your heat is built consistently between first and second law. And in your second law, entropy appears. Now, with this new definition that you have, which is observational entropy, right, how does this affect what the definition of heat is, and so on? It will affect even probably the definition of work. Have you looked into these things, and how does this actually come about?
Yeah, so there are many different definitions of work in the literature, and I wasn't I wasn't the one studying them. Mostly, I studied isolated systems because the question was, what is the meaning of second thermodynamic law? Yeah. And second thermodynamic law applies only in isolated systems. When you talk about work, you really discuss open systems, or depending on your definition of an open system. Basically, some system where either it has open system dynamics, it's a master equation, or your Hamiltonian is time dependent.
Right.
And that was studied by Philip Strasberg. I can reference you to this work, but my understanding of his work shows that he considered a system which is connected to a large Römer bath. So you have a large thermal bath and small system that you are fully able to control. So the large thermal bath, we assume it's in some thermal state. It doesn't need to be Gibbs state, but it makes for nice math. And the small system you can fully control, and you are able to change the Hamiltonian of the small system. So depending on how you change your Hamiltonian, you can add energy or extract energy out.
Mm-hmm.
What he found, with this idea that he mentions, well, if you put your food into a microwave and you press the button, you don't say, I'm performing work on the system. You're just saying, I'm heating my food.
Mm-hmm.
So there's this idea of work being defined as the change in the mean energy of the system. But with this idea, this microwave, am I really performing work there if I just heating my food? Not really. Mm-hmm. So how do you define work differently? And maybe the work should be the part of energy that's somewhat useful in some way. And this is exactly what he tackled. He studied the scenario where he has some small system and he has time-independent Hamiltonian, which introduces some energy into the system. And then he studied how much of that energy goes out to the thermal bath and how much of that energy stays in. And the part of energy that stays in, and assuming that he's perfect control, he can again extract that part of energy that stayed in. So he actually divided total energy with some physical motivation into two distinct parts, and he has a definition there. This is what work is. Mm-hmm. That's the part of the energy that you insert into the system, but afterwards you can still extract it, while heat is the one that escapes to the thermal bath.
Okay. Yeah. Thank you for that. We have another question, Sarika.
Hi, Dominic. It was a very nice talk. I have just one question. Suppose you have a chaotic system and then you have a corresponding random system. For suitable partition, they will both yield the same entropy. If we have some generating partition which maximizes the entropy, both systems will have the same entropy. So is there any way to know about the system? Like chaotic system means it is the deterministic system, and random, which is just a random system. So is there any way to know that by looking at the entropy, that whether it is for a deterministic system or for a random system, for example? So does entropy,
so that your question,
some idea about, maybe.
So if I rephrase this, your question is about if you look at this observational entropy, can you determine whether it's deterministic or stochastic or not stochastic?
Non-stochastic, and perhaps. Yes.
Well, that's a good question. I think in a way there is, but that depends on your master equation that describes your evolution, right? So very commonly a Lindblad equation, or the ones that usually assumed in this system with infinite thermal bath, weakly interacting with your subsystem. So you have this Markovian assumption that whatever goes into the bath is lost there, but it doesn't affect the bath itself because it's infinite. And as a result, your state will converge to the thermal density matrix at the temperature given by the thermal bath. And you will never see Poincare recurrence time.
A Poincare recurrence you see in chaotic system. Chaotic system means they are embodied. Really? So Poincare recurrence theorem still holds good for chaotic systems. For continuous system.
But I think you were mentioning stochastic. So maybe
no. Sorry, my question was chaotic and stochastic. So chaotic systems follow Poincare recurrence theorem because
I get it.
You leave and then your trajectory has to come back because it's ergodicity property. So
I get it.
Chaotic system have a Poincare recurrence theorem. So
Then I probably don't understand the difference between the two.
Okay. Anyway,
maybe could you rephrase the question maybe?
My question was very simple, of course, like random system and chaotic system for suitable partition, they will give the same entropy. Now the question is, by looking at the entropy or what other measurement you have to do in order to understand whether this entropy is produced by a random system or a corresponding chaotic system. Like I can give very simple example of logistic map. Logistic map for suitable generating partition, transition entropy is same as the exactly same random system. Corresponding random system means like density of the state is following the same as for the logistic map. So they will give you same entropy. Now, the question is like now what information entropy can give us for the system from which it has been generated.
Okay, yeah, I think I can, well, maybe suggest an answer for you, since I don't know about classical physics that much. Okay, but given this definition, you see this observational entropy depends only on these probabilities and on these volumes.
Yes, yeah, probability and volume. So one can define this transition probability for logistic system and the random system, like logistic map means 0 to 1, and here random system 0 to 1, and you give density of states kind of like in classical term, which is logistic map, which is like reverse hump kind of thing. And you will get the same entropy if you have generating partition. What does it mean? Like generating partition means you put it 3 by 4. So the same like pi ln pi summation over all I for
exactly. Yeah, I think that's the point.
As random corresponding random.
Right. So I think that's the point that I was wanting to make. So the volume of the macro state really depends on your system. It's basically given by your cousin. It's a collection of numbers. So this doesn't change, right? The only time dependence comes in these probabilities. So if there is a way distinguishing these two models, the chaotic from stochastic, it must come from the different behaviors of these probabilities. If these probabilities behave exactly the same, there's just no way how this entropy can distinguish the two.
But I'm sure there must be some way. Anyway, thank you.
Well, if the probabilities are behaving differently, then there would be, yeah. But this entropy would not be able to do that. You could, if you look at phonome entropy, I'm sure you will. Phonome entropy basically assumes full information about the state of the system, and that the one will tell you much more. But this will not.
Okay, thank you.
Okay, great. Any other questions coming up? I guess not. So let's thank our speaker once again.
Thank you.
And I think I will now end this meeting here. So I request at least everyone, Dominik, please just hold back, and the other group leaders as well. The rest I would ask to leave. Thank you all.
Thank you.